All right. So good morning. Welcome to class. Today is the 11th and actually the last lecture of the course. And today the topic will be about uncertainty and how to estimate and deal with uncertainty in neural networks. So we'll divide the lecture today in 4 parts. The first one, in the first part, I will tell you about uncertainty and try to give you some intuitive explanations about different sources of uncertainty. Then we'll consider a first type of uncertainty, which is called aleatoric uncertainty, and we'll see how to capture this kind of uncertainty when it comes to neural networks. And then we'll consider a second source of uncertainty, which is called epistemic or model uncertainty, which basically represents your lack of knowledge or your ignorance about what is a good model. And finally, we'll see a topic which is connected but still a bit orthogonal to uncertainty, which is adversarial attacks, and which will reveal that the kind of networks we've been talking about together are prone to what is called adversarial attacks, and basically we can make them change their predictions with only a few and well-adjusted perturbations to the input. And I include this topic today because to me this also relates to a more general notion, which is about robustness, which you can achieve when you incorporate uncertainty in your model, and the robustness is also related to adversarial attacks because you would like to, of course, to be robust to these small changes. All right, so I will start with a quote from Carl Sagan, who was a physicist, and it goes as follows. So he says that every time a scientific paper presents a bit of data, it's accompanied by an error bar, and this error bar is a quiet but insistent reminder that no knowledge is complete or perfect, but rather that this knowledge or that the error bar that comes with this bit of data is a calibration of how much we trust what we think we know. And that's precisely what we'll try to do today. We'll try to estimate and quantify the uncertainty that we have about, for example, the predictions of the neural networks. And to me, this is something, which is, of course, very important in deep learning, but it's also fundamental, actually, for any scientific disciplines. And when I say scientific discipline, of course, I include engineering disciplines as well. If you do an analysis and present results, it's really necessary that you include error bars, or that you include, that you specify how uncertain you are about the result that you present. And when you do this exercise, you should try to include as much as possible of the known unknowns that you know about the problem. And so these known unknowns may be about, for example, the fact that you use an instrument to make measurements and collect data, but this is not perfect. You will be able to collect data up to some precisions, or there will be plenty of things that maybe you would have liked to measure, but you cannot. You only have access to a certain type of measurements. And so that means maybe there are things that you wish you had known, and if you had known them, then you would have maybe have produced more accurate predictions. But you know that you don't know them, so you should account for this ignorance. And calibrate and estimating your uncertainty is a way to do that, right? So this is one type of uncertainty. Another type of uncertainty would be, for example, the fact that you are postulating a model, for example. So today we'll postulate that we are dealing with neural networks, but we don't know exactly, for example, what should be the best parameters to use. And maybe we have some prior knowledge about that. Or maybe it's about even the structure of the model itself, the set of equations that make up the model, you could also put some uncertainty on top of that, right? And then account for this uncertainty when you present results. So for example, I don't know, if you take the laws of motions and use the acceleration for the gravity, you could know it up to some precision, but you know that you will not know it exactly, right? And the fact that you know that, you should account for this when you produce your results. And so to me, so this is really an important thing that you should remember, please, when you do an analysis. For example, when you will do your master thesis or even in the project for this course, you should, when you report results, you should also tell the reader that there are things you don't know, but you are accounting for that, right? And therefore, and the reason is that if you, and even as a reader, if you see some scientific results which are just point estimates and with no uncertainty around these values, then in my opinion, it's revealing of the analysis to be very naive, and you should really be cautious about the interpretation of these results. As soon as you show that there are plenty of things you don't know, and there is some uncertainty about this value, then you have a much more nuanced and nuanced discussion about this result. All right. So let's dive in and let's talk about uncertainty. And why I think it's important in the case of deep neural networks. So I will just consider two very concrete use cases where if we had known, if the models that were used had come with uncertainties, then maybe they would have taken other decisions. And so the first one is the example of a Tesla using the autopilot system. And in May 2016, there was a first accident, a first fatality due to some misbehavior of the system. And the reason, so basically the scene is like this. So you have a Tesla going from the left to the right in this direction. And then at the same time, in the opposite direction, there was a truck going from the right to the left, but then turning here to the left, to its left, right? And what happened is that the car, the Tesla didn't stop because it confused so this is the truck, this is the car after the crash, because it confused the white side of the truck for just bright sky. And so if the car is just seeing sky, then it can go forward. It was thinking that there was nothing, there was no obstacle in front of it, right? And because of that, it went through, and you can guess about the final outcome of this. Another example, another use case, which unfortunately Google is quite famous for. So in an older version of one of their image classification system, they were which were just about a naive and maybe innocent application of a classifier, right? Where you just present images as input and what you want as output is a category. And what happened is that, well, for example, this image, skyscrapers, they were correctly identified as skyscrapers, the same for airplanes, cars, and so on. But for this image that you see in the bottom, at the bottom row in the middle, these two guys which are black people, were incorrectly and quite wrongly misclassified as gorillas. And of course, this shows and highlights some strong bias against these people, and this is something that you don't want to happen, of course. And so one of the message and one of the reason I'm talking about uncertainty is that if both these algorithms were able to assign a high level of uncertainty to their erroneous, in this case, predictions, then maybe the system may have been able to make better decisions and likely to avoid disaster. Right? So by that I mean, if the system is telling you, okay, I think this image is of class gorilla, and I'm 99% that this is gorilla, then okay, you would maybe show this prediction or use this prediction to make a decision. But if at the same time, if on the other hand, for that image, the system is predicting gorilla, but maybe only with a 20% confidence, then maybe you in this case, that would raise some warnings for the system, and maybe it would decide not to rely on this prediction, because the uncertainty is too high and the risk of making a wrong prediction is too important with respect to the benefits of that could happen if that was actually a correct prediction. So of course, it's always a trade-off between between making correct predictions and profiting from the reward that you would get from this, and making a wrong prediction and then having to pay the price for this incorrect prediction. All right, so let's dive into the two. I mean, I say the two, but there are others, but two main types of uncertainties. The first one, let's consider, for example, this setup where we would have like a classification problem where we are given images, and what we want to do is to train a classifier, a neural network, to say if the image is of a cat, of a dog, or of a cow, and so on and so on. But what is special about this dataset is that maybe some of the images, like for example these two for the cats, are noisy because of the acquisition instrument that we are using. Right? For example, we are using quite old camera, or the conditions during which the photos, the pictures were taken are not that good, so there is some noise, and and maybe this noise will propagate to high uncertainty when it comes to deciding whether this image, for example, is from a cow, a dog, or a cat. Right? And so this is an example of what we call aleatoric uncertainty, because it's some kind of noise or randomness which is due to the process itself, right? And or to the fact that you are using an instrument or measurements that are imperfect, and that cannot capture the true reality of what you want to measure. A second source of uncertainty is what happens when you are given some data, and then you are postulating a model, but you, as a good scientist or a good engineer, you know that this is just a model, right? And so there are things about this model that maybe you are uncertain or more or less uncertain about, and that you would like to take into account. So, for example, if I'm giving you these textbook situations where I show you these points, and I show you these two models, the one on the left in blue, or the other one on the right also in blue. Which one should you pick, right? What are your prior beliefs about what is a good model for this kind of data, right? And so when you make this decision, right, what you are basically, because intuitively, what often, if I could have asked you this question in class, I'm quite sure most of you would have told me that this is a better model than this one, right? But for which reason, this is not so clear. But actually, implicitly, what you are saying is that, okay, there are several models that could fit this data, and I come with some prior beliefs. I think, and this is really subjective, that this one is more appropriate than this one. And so this kind of uncertainty is what we call epistemic uncertainty or model uncertainty, right? And they capture your ignorance and your beliefs about the models, either from a structural point of view or from a parametric point of view when you decide a structure for them. So as an example of these two sources of uncertainty, I've taken this picture from a paper from 2017, which is about segmentation of images, as we have seen in lecture 6. Right? So you are given some input image, and what you want to do is to segment this image into regions that are semantically equivalent. Right? So you want to say that this part here corresponds to sky, this is the road, this is pavement, and so on and so on. And so what this shows is that if you train a neural network, and if you try to quantify its uncertainty and try also to decompose this uncertainty into aleatoric and epistemic uncertainty, then this gives you some quite good insight about why the model is maybe making wrong predictions in some regions, or where the model is actually uncertain about its prediction. And so what the caption says is that our model exhibits in this column in D increased aleatoric uncertainty. This is the high aleatoric uncertainty correspond of course to bright regions on object boundaries and for objects far from the camera. And indeed, this is precisely the definition that I've given you. Aleatoric uncertainty may come, for example, from the imperfections of the instrument. And typically, for a camera, the deeper it sees, or the further and further away it sees, the more noise you will have, right? And this corresponds to the regions that have higher uncertainty. They correspond to regions in the sea that are very far away. But that's also true for the boundaries between objects, because, for example, if you look at this car, and indeed you have higher uncertainty around at the borders, at the boundaries, because for these pixels, you don't really know if they belong to the car or to the scene which is further away. So it's expected that if you have to assign a class to these particular pixels, that you are not quite sure if they correspond to, for example, the road or the car. But if you had, on the other hand, maybe at a better camera, then of course you could have resolved some of this uncertainty. Then we have epistemic uncertainty, and they say that epistemic uncertainty accounts for our ignorance about which model generated or collected data. And this happens, for example, here, where they say that our model exhibits increased epistemic uncertainty for semantically and visually challenging pixels. And indeed, for example, this region for which the model has high epistemic uncertainty corresponds to pavement. And when you think about it, it's quite natural that you have higher uncertainty there for this class, because it's maybe more challenging to distinguish between pavement and road, right? Because semantically, they correspond to ground, and making the difference between the two is maybe not that easy, right? But if, for example, the model was trained on more data, this is an uncertainty that could vanish, because then the model would have been able to really get the concept and grasp the semantic of this class. Right? And finally, a third use case, which I think is also quite important to remember, is let's say that you did a project, you have trained some nice neural network. Sorry. Maybe what you produce is a classifier to classify different breeds of dogs, and it works very well on this data and even on this data that you have considered. But let's say then I ask you to use this same classifier to classify this image of this grumpy cat. What do you think the model will produce as output? What you would want it to produce is maybe that it's not confident that this is a dog or any of the dog. So there shouldn't be any prediction for any of the classes of the dog that comes with high confidence. That's what you would expect. But actually, if you do that, it's very likely that it will actually put the density and most of the density in one of the classes. And this is a case of out of distribution test data. And the behavior actually of neural networks on out of distribution test data, unfortunately, is often arbitrary or actually just implicitly specified by the inductive biases that you put in the architecture, but which is not easy to understand it, to be, and it's not easy to predict what will happen on test data. So generally, you can say it's arbitrary, and who knows what will happen. But this is also very important, because if you ever have to deploy a real system in your next in your future jobs, you should remember that maybe there is a neural network behind that you've trained on some training data, and this training data was collected under some set of assumptions, right? And then you produce a neural network that works well under this set of assumptions. But when you deploy the system, you should make sure, of course, that these assumptions remain true. If there might be situations where where these assumptions may become violated, then who knows what will happen. All right. So I will, as I said, so this is for the motivation. Now I will tell you about these two sources of uncertainty in more details, aleatoric and epistemic, and we'll see how to model them in neural networks. So as I said, aleatoric uncertainty basically capture noise which is inherent, intrinsic to the data generation process, and therefore to the observations that you collect and that you use, for example, as input to your model. And so, for example, sensor noise, due, for example, to the limitations of your camera, or motion noise will result in uncertainty. And what is important to remember or to understand is that this type of uncertainty cannot be reduced with more data. It's not because you go from a training set of 1,000 images to 1 billion images that you will manage to reduce this uncertainty. No? And you will not be able to do that because this uncertainty is intrinsic to the process, to the thing that you are observing, right? And it's not because you are observing it more than this randomness reduces, right? But maybe they are part of this uncertainty that could be reduced if you had access to better measurements or better equipment to study this process. But then that would also lead to different kinds of observations of a new nature, I would say. Then we can further categorize aleatoric uncertainty into homoscedastic and heteroscedastic uncertainty. So homoscedastic basically means that the homoscedastic aleatoric uncertainty basically captures that the uncertainty that a particular task might cause, right? And this will stay constant for different inputs, while heteroscedastic uncertainty will depend on the inputs of the model, with some inputs potentially having more noisy outputs than others. It's just saying that in one case, the randomness is assumed to be the same, whatever the observation, while in the other case, you are saying that this randomness, this uncertainty, may fluctuate depending on the particular input. So it's as saying if it was some kind of stationary uncertainty or non-stationary uncertainty. So this is an example of these two of these kinds of aleatoric uncertainty. In this case, what we would say is that, or that what we would assume, or what we would have in the process, is that the uncertainty around the observations is small and constant. Regardless of the inputs, the size of the uncertainty, the size of the error bar of these regions is the same, more or less. Of course, in this case, it's estimated, but the two, you'd force it to be the same, and it would be small. Or you could have the same, but with, so still homoscedastic uncertainty, but with a larger variance, and you would be in the second situation. Or you could say that, no, I assume that I have a heteroscedastic uncertainty, right? Meaning that I'm allowing my model to, and the uncertainty to change depending on the location, depending on the particular inputs that I'm looking at, right? So for example, you see that in the region in the middle, uncertainty is small, and you see that on the left, uncertainty is larger than in the middle, but it's at the same time smaller than the uncertainty for the right region, which is even larger. Right? So what you see, so what I mean is that basically the size of these error bars is allowed to fluctuate with respect to the input x. But it was not the case here or here. All right, so how can we do that with neural networks? So today we'll mainly assume regression task. So when you are given an input, you want to predict an output, which is typically a real value, right? So x, as usual, is a vector of p dimensions, p elements, and y is just now a scalar value. And we want to predict or to try to quantify or to estimate rather the conditional value of y given x, right? So we can incorporate aleatoric uncertainty in our model if instead of just trying to predict the scalar value y or trying to predict a single point estimate y given x, we try to predict the full distribution, the full conditional distribution, py given x. Right? And so for example, we could assume, and this is a choice that you make as a modeler, we could say that I think, or I believe that this conditional distribution py given x is, or that y is normally distributed along some value mu x, which is, so it's a value which is a function of the input x, and with some variance sigma squared, which is also a function of the input x. Right? And of course, since this is a course about deep learning, what we'll do is that we'll specify both mu and sigma squared as neural networks. Right? So this is a bit different from maybe what you are used to, in the sense that, again, I really want to stress this, that we do not wish to learn a function f of x that would produce a single point estimate y hat for this particular input. Right? What we want is to say that, okay, I know that I want to predict a y value, but I do know also that I will not be confident, or I don't want to trust just one single point, one single value that this function could produce. I want to capture the whole range of values that y could take given this input x, right? And this is why we are basically lifting the problem to the problem of trying to model a full conditional distribution py given x. All right, so if we say that mu and x and mu and sigma square are neural networks, then in terms of graph of computation, we would have something which maybe looks like this in the case of homoscedastic aleatoric uncertainty. So remember, when we say homoscedastic aleatoric uncertainty, we are just saying that basically sigma squared here is actually not dependent on x, and it's just a parameter that we would have to learn, but that parameter would be shared across all input x values. Right? And so in the end, only the mean mu would depend on x. And so if we model this conditional, or the parameters of this conditional with a neural network, and then want to evaluate the conditional distribution py given x, what would happen is that we would feed x to some neural networks, and the architecture of this network is, you can use anything that we have seen together, depending on the nature of x. So if x is an image, then the neural network could be, for example, a convolutional neural network. If x is a sequence, you could use a recurrent neural network, whatever. This would be specific to the data that you get as input. Then this neural network would come with some parameters, theta, but we would architecture also this neural network to produce as input a value, in this case, for example, a scalar value, mu, and we would use this mu value to parameterize a normal distribution, and would say that the output of the neural network is the mean of this, for example, normal distribution. And the variance of this normal distribution is specified by this parameter sigma squared that I would have to learn as well. And now that I have these two values, the mean and a variance, that these two parameter values together specify the full conditional distribution py given x. And so I can take any y value and look at its density p. Okay, by just using the expression of the probability density function that we know for the normal distribution. So. Okay, then the question is, fine, but how do you train this guy? Well, actually, we'll use exactly the same recipe as before when we derive our loss function for classification. So I see there is a question from Jonathan. Is it the same neural network that would put mu and sigma, like for instance the decoder, or is it two different neural networks? Okay, so we are not there yet. So at the moment, sigma squared is just a constant parameter that we'll have to learn. So the neural network does not produce as output the variance. And we have only a single neural network that produces as output the mean, in this case mu x, this guy, and is used as the mean for the normal distribution. And we are doing that because we are in the case of homoscedastic aleatoric uncertainty, where we assume that the variance basically is fixed or is shared and across all input values x. But indeed, we'll see just in a few slides that this parameter can also be produced as output to the same or to a different neural network. All right, so how do we learn this? So what we have to learn are the parameters theta of the neural network and the sigma squared variance parameter. So what we'll do is that we just do regular maximum likelihood estimation, and we say that the parameters that we want to use are the parameters theta and sigma squared that maximize the likelihood PD given the likelihood of the data given these parameter values. Again, if you assume ID data, then this joint likelihood over the entire data set can be factorized as product of individual likelihoods over the elements in this data set. So in this case, the XY pairs that we have in the data set. And each one of these likelihood factor correspond to the conditional likelihood of the yi value given that particular xi value for those parameter values theta and sigma squared. Here we have said that this conditional is a normal distribution, so you know the density function for that distribution. You can rewrite it in this way. So you have this factor that depends on sigma that we have to learn, times the exponential of minus the square distance between the value yi and the mean, in this case mu xi, which is the output of our neural network, over 2 sigma squared. So this maximization of a product of these densities can be is equivalent to the minimization of the log likelihood. And so you can transform this optimization problem as the one of minimizing now over the parameters theta and sigma squared the sum of the log likelihoods. And so in this case it's nice because the product transforms as a sum, these factors transform as terms, and this exponential, when you take the log, disappears, and you are left with minus the square distance over this factor. And since we want to minimize minus the log, the minus disappear, they cancel, and we are left with this expression for the loss function. So what you see there is that so first let's maybe see if sigma square was not something we wanted to learn, and if we just said a priori, for example, sigma square is set to some values that I know or that I believe, let's say 1, then the minimization problem would be equivalent to just, so this would be constant, this would be constant, this would be constant, so everything could be removed from this expression. That would not change the solution of the minimization problem, and actually would be left with the good old mean squared error between the output of the neural network and the yi values. Right? And so this is something I think I've said already, but this squared error loss can be seen as a consequence of first postulating a generative model. So in this case, we would be postulating a normal distribution between for the conditional py given x, and then following the principle of maximum likelihood estimation. Okay, so now I can move on to the to the case of heteroscedastic aleatoric uncertainty, and to the question and back to the question of Jonathan, in which now instead of predicting only the mean of the normal, we would also be predicting the variance sigma square. So, and here there are different things that you could do. You could either have a single neural network that take x as input, and then this network has two different heads, two different outputs, one for the mean and one for the variance. And I think here that makes sense because usually at least the first layer that are used to process the input data are very likely to be very common when it comes to predicting the mean and the variance. And maybe you could add some complexity. So you at some point in the neural network architecture, you could fork and then maybe add a few layers, a few more layers for each of the two paths, and then finally predicting mu and sigma square. You could also have two distinct neural networks, but I think you will not profit from this shared computation and maybe and very likely the same shared information that you should extract from X to predict these two values. Right? But other than that, the story remains the same. We have two parameter values that are produced as output to the neural network, one for the mean, one for the variance, and then we plug them into the into the expression of the probability density function for the normal distribution, and from there we can evaluate the density at any y, and that gives us some value p. In terms of training, it's also identical as before. We could proceed by maximum likelihood estimation, except that now we would only be optimizing for the parameters of the neural network, because the variance is no longer fixed and no longer learned. It's given, it's produced as output by the neural network. You will have the same development as before, except that all the sigma, the occurrences of the sigma symbol have been replaced or upgraded by occurrences, by call to the function, or have been replaced by a function sigma, which argument is the input xi. All right, and so we are left with a similar expression. There is a nice effect of this either homoscedastic or heteroscedastic uncertainty when you try to understand what the purpose of the variance term that appear in the loss. And so on the one hand, so you want to minimize the loss, right? So there are several ways you could do that. But let's say that the prediction, the mean prediction, so mu xi, is very far away from yi. Then in this case, the square difference will also be very, very large, right? But you can and so they will dominate. They will have they will dominate in the loss that you want to minimize. So a way to minimize this, or actually to be less penalized by this wrong prediction, is to increase is to increase the variance term, because if this this term, the squared variance, is high, then this whole fraction will tend to 0, right? Because this is a positive quantity, which would be large, okay? But if we manage to increase this variance further, then that would shrink the whole thing towards 0. And in this case, even though you would be making a wrong prediction, you would say that, or the network would basically, the effect would be the effect that would have is that the network at the same time would say, I believe there is a high variance that comes with this prediction, this mean prediction. Or in other words, that I'm quite uncertain about this prediction that I'm making. Right? And you see that acknowledging for the fact that you're uncertain is actually a good thing, because that will decrease the overall value of this term. Right? Of course, you cannot do this to the extreme, because you could just say that I'm very uncertain about everything and I'm maximally uncertain about that, right? So the variance would be infinite. But of course, then the prediction that you would have would be pointless. It would just be garbage in terms of the mean. And so to compensate for this other effect, you have this other term, the log of the variance, which will try to keep the variance at the same time as low as possible, right? Because log of the variance will be typically, that will be some it's just a monotonic increase. It's just an increasing function of the variance. And so the way you could minimize this term is by forcing the variance to be as low as possible, right? But if you do that, so if there were only this term, of course, then the network would learn that it should just say that everything has low variance. But if you do that, and if you do that at the same time as you are doing that, if at the same time this variance term now is too low, then it could also amplify the error that you are making. Or the weight that this term has in the total. So the training will find the trade-off between these two effects until it finds the optimal, some optimal solution. All right, so now let's move on to another problem, which is the fact that so far we've assumed that this conditional py given x is something as simple as a normal distribution. But of course, for most interesting real problems, this py given x will be a distribution which is likely to be more complicated than just a Gaussian distribution. And in particular, it might be that the conditional distribution of the output is not unimodal, but could have different modes at different places in the density. And so this is one example where so imagine again that you are implementing a system for a self-driving car, and what you want to predict what you want to predict. So the y value would be some reward that you get given the steering action that you do. Either that you, for example, you are turning left, or you are turning right, or you are just going straight ahead, right? So for every different angles for the continuum of steering actions that you could take, you could compute some expected reward that you would obtain, right? And in this situation, of course, what you would like the system to do is just to avoid driving over this big hole, right? So so typically if you go left, that would be fine. If you go right, that would be fine as well. But if you just go straight ahead, then that would be terribly bad. And so if you look now at the value of the action that you could take, you would have different. You would have two modes in this case. Of course, this is a fictitious and simplistic situation. But what I'm saying is that now if you have this two mode and then minimize for the mean, then the optimal action with respect to the mean would be to go just straight ahead, and that would be wrong because and the reason is that your model assumptions are wrong. The fact that you would have assumed a unimodal distribution for the value of the action would not be appropriate given the actual nature of the value of the action. Okay, so there are plenty of cases where basically what you would like to just have is to put more capacity in the distribution, in the conditional distribution that you assume for py given x. So a very simple model and quite powerful model that has more capacity than a single normal distribution is just to say that you will consider several distributions together, several normal distributions together that you will sum into a mixture distribution. So this is what we call a Gaussian mixture model, or a GMM. And mathematically what we would say is that we define the conditional py given x as a mixture of k other Gaussian or normal distributions, right? Meaning that effectively we would say that py given x is a sum from k equal to 1 to k, the number of components, the number of elements in the mixture, the number of normal distributions that are making up the mixture. Each of them can be used to evaluate the density of y for their particular value of for the mean and the variance, and then they would be mixed together and weighted together by some mixture coefficients pi k, which are just value between 0 and 1 and such that they sum to 1. So for example, you see here in the plot at the bottom, we are considering a mixture of 3 Gaussians. We have a first Gaussian here with the dashed line, another here with this other curve in the dashed line, and then finally a third here. And if you look now at the sum, the weighted sum of these 3 guys, then we obtain the distribution in black, of the density in black. And you see that this model, potentially, of course, that will depend on how many components you put, but you will be able to capture more modes if you need to capture more modes in the conditional distribution. All right. So this is something that you can do, of course, also with the neural network. So and the trick or the philosophy is still the same. You start with a parametric model for the Gaussian distribution, for the conditional distribution Py given X, except that now it's no longer a unimonal normal distribution. It's now this mixture of k Gaussians, right? And so what you will do is that you will use the neural network to produce the parameters, except that now we'll have more of them that you should use as input to specify fully that parametric distribution, that in this case, that Gaussian mixture model. Okay, and so if you assume a model, a GMM with k components, let's say 10, then what you will have is a neural network that takes as input X as before, but produces as output 10 values for the means, because we need 10 different values for, or we need we need one mean value for each one of the 10 components in the mixture. Similarly for the variance, we need 10 values, so that would be 10 more outputs to the network. And finally, we would have also to predict the coefficients, the mixture coefficients by k, and that would be 10 more outputs. So typically we would have for this model in total 3 times k outputs for the network, right? But once we know the values for these outputs, for these parameters, then we can just plug them in all into the expression of the GMM, right? And once we have that, then we can evaluate the density under this distribution for any input y, and that would give us the density value p. Okay? And you would train this thing exactly in the same way as before by doing maximum likelihood estimation on the parameters of the neural network. Okay, so before the break, let's just consider a very simple example, but even though it's simple, it's also highlighting the issues, these particular issues of multimodality in the output. So let's consider that we have some training data which is generated randomly in this way. So for example, we would have y values that are sampled uniformly on the axis, and then we would say that for the purpose of this problem that y is generated as xi plus 0.3 times the sinusoid of for pi xi plus some noise epsilon I, which would be drawn from a normal distribution. Okay, and so if you plot this data, if you generate y values or pairs xy values or pair of xy values, then you would obtain the kind of points that you have in blue. And then if you fit a simple two-layer network that would produce just point estimate for y by, for example, minimizing the squared error loss, then you would have for the predictions, the predictions that you see in red. So let's do that. It went very fast. As you see, with the red curve are the predictions as the network is training with respect to the number of epochs. And you see that eventually you get predictions that are just in the middle of the points that you have in your training data, because that's precisely what you are aiming for when you just minimize square error. You are just fitting basically the mean of a normal distribution, and you are saying, as I said, that the variance is fixed. But you assume that it's just one single normal distribution and not a bunch of them that you would stack together. All right. So now what happens is, what do you think? So what is interesting to notice is if we flip the x and y values, right? So if we say that the x values become the y values and that the y values become the x values, and try to just train the same network as before, then this is what we would obtain. So what we want is from the x value now to produce a y value. But since we've flipped, now by doing this flipping, when you look at the actual conditional distribution of y given x, then there are different modes, right? For example, if we are at this x value, then there are three regions or three regimes of value that the y variable could take, either a value here, another value in this region, or maybe a value in this third region. But of course, if you are naively trying to fit a single point estimate, then what we would basically have as output to the network is the mean values of the y's for some particular x, right? So for example, here in this region, with the y values can only take a value here or here, and sorry, and therefore the mean is something in the middle, but that something in the middle is a wrong prediction, because it's very far away from actually from the data that was given as seen during training. And the only place where it works is here around 0, 0, because of course there is only one mode, and in this case it would make correct predictions. But as soon as you depart from this point, then it does not work anymore, because you enter regimes where the conditional has multiple modes, but of course that you would not be able to capture with just a single point estimate. Okay, now let's see what would happen if instead, same data, same problem, we try to fit a mixture density network. So this Gaussian mixture model, as I've introduced just before. Again, otherwise the neural network is just the same two-layer MLP, but with more outputs. So what you see now is that, and so the red points correspond to random samples from the conditional, so the approximate conditional. So which is given by the by the Gaussian mixture model that's specified by the outputs of the neural network, and then you sample points from this. So that's why it's a bit flickering like this. But you see that it's working quite well overall. So if we look at the same regions, the mixture density the mixture density network is correctly putting density for the y values in these regions and in this region, and nothing in between as we had before when we were just trying to predict one single output. There are still some issues, which may be due to the architecture or to the number of components that were chosen for the mixture. As you will add more and more components, you will get better and better, of course. You will get more and more capacity, and that will allow the network to fit better and better to the training data. There are maybe also some architectural limitations of the fact that it's just a 2-layer MLP, which is maybe not wide enough. But overall, it's doing quite a good job at capturing the different modes. And the fact, also if you notice, that there are regions where there are only 2 modes, there are regions where there are 3 modes, and there is one region where there is only 1 mode. And this is correctly captured because, let me go back to the slide. Because one of the output of the network is the mixture coefficients. And so if the neural network understands and learns that for some values of x, there are just one or a few modes, then it can basically disable some of the components by predicting, for example, values for pi k, which are close to 0. In this case, would fall back to, for example, a unimodal or bimodal distribution, even though it could use more capacity to model something more complicated. All right, so perfect. I think it's a good time now to take a break. Let me go full screen. And we'll resume in, let's say, 12 minutes at 10:45 for the second part about epistemic uncertainty. Okay, we'll come back. So before we start, I will just answer another question from Jonathan, who is asking, the Gaussian mixture approach enables to learn the PDF of a multi-random variable distribution. Thus, it could be used once the PDF has been estimated to generate sample from this multivariate distribution. Yes, that's correct. But just two things to clarify. So in everything I've said today, I've assumed that y was some scalar value, and therefore that py given x is just a univariate distribution. But of course, you could upgrade this to multivariate distributions by saying that y now is taking vector values, and then upgrade the univariate normal distribution to multivariate Gaussian distributions, and the story would remain the same, except that each mu k would be upgraded also to a vector. The sigma squared k would be upgraded to covariance matrices, and the coefficients would remain scalar values. But other than that, it would work similarly. And indeed, you could use that then to model multivariate distribution if you wanted. And since this model is also something that we can sample from, right? Given a multivariate Gaussian distribution, we do know how to sample from this distribution. Then, of course, that means you can also generate samples from this conditional py given x. And that's precisely what they are doing here in this plot. So the red points are samples from this conditional distribution. And they've been drawn, of course, because we can draw from this distribution. So you could use that as a model, and it's usually a good baseline to evaluate every time you want to model, I would say, simple distributions. But if really there is some more structure in those distributions that you want to model and to learn, and if not only you want to have access to the density and to the fact that you want to be able to generate data out of this distribution, then in this case, you should, in my opinion, then fall back to the kind of generative models we've been talking about for the last 2 lectures, like VAEs, that allows you to do that, GANs that allows you to sample, but you will not be able, of course, then you will not have access to the density. There are other examples of generative models that I've not talked about in this course, but for example, normalizing flows is another family of methods that you can use. And these models are quite nice because they give you access to the density of any point under this distribution, and to the fact that you can also sample out of this distribution. And today's progress on normalizing flow allow you to model multivariate and quite complicated distributions, like for example distributions on images, very high dimensional distributions, and they work quite well for this purpose. All right, so now let's move on to epistemic uncertainty. So epistemic uncertainty is another source of uncertainty, which is quite different from aleatoric uncertainty, in the sense that this uncertainty does not capture something which is inherent or intrinsic to the process that you are trying to model, but it accounts for your own ignorance as a modeler. It's just basically stating everything you know you don't know, but that you want to account when you are making predictions. And this ignorance can be either about, for example, which model is the most appropriate to model the data that you've collected. And so you could say, I don't know, like, let's say you want to fit a polynomial, but you don't know the degrees of the polynomial that you should use. So that's more like a structural ignorance because you don't know the degree of the polynomials. And then you could also have parametric epistemic uncertainty when you've decided on a class of models, for example, polynomials of degree 3, then you still have to account or to estimate or to estimate typically some parameter values that you should use for this particular class, right? So in this case, the coefficients, the 4 coefficients that make up polynomials of degree 3. Right? And so epistemic uncertainty accounts for both of those. It's a type of uncertainty that can be explained away as you get more and more data. And it's also often referred to as model uncertainty. So in this course, of course, the models that we've been talking about are neural networks. And what we'll try to do together today is to define or to say that, okay, I'm assuming some neural network to capture this phenomenon between input and outputs, but I still do know that I'm quite uncertain about, for example, the parameters that I should use for this architecture, right? And so what we'll do as good Bayesians is that we'll model our ignorance, for example, about the parameters of this neural network by defining a priori a distribution over the weights of this neural network. That will be our prior distribution that I will denote today as pi omega over the weights of the neural network, right? It's just stating that, okay, I'm not looking at the data yet. I'm just assuming without knowing anything, or I come with some prior beliefs that, okay, this is the model I'm choosing. It's a neural network, let's say a 2-layer MLP or a ConvNet or whatever. But I do know that I don't know what are the best parameters or what are good parameters for this network. And this uncertainty will be captured, or this ignorance will be captured by this prior distribution that you specify on the weights of the network. Okay, and once we have defined this prior distribution, then we'll get access to some training data, and we'll use this training data then to derive the posterior distribution over the weights. Right? It's as if you start with the prior, you get some observation, then you update your prior given this observation to produce the posterior distribution. And that's what we'll do, except that we'll have now a posterior distribution over the weights of the neural network. And then we'll use these updated beliefs on the neural network parameters then to derive what we call the posterior predictive distribution, because at the end of the day, of course, we'll still want to produce some outputs, some y value, or some, in this case, some conditional py given x. But what we'll do is that we'll want to do so while accounting for our uncertainty about, in this case, the model parameters. Okay, so let's dive into the mathematical details. So first, I will define the prior predictive distribution, and which simply amounts to defining the conditional py given x, right, as the integral over all possible configurations omega of the neural network, and then for each of them to compute the conditional py given x. Then you would just aggregate them all in this big integral, and that would correspond to the prior predictive distribution. It's the prior predictive distribution because we are weighting all these different parametrizations of the neural network according to our prior beliefs about the parameter. Right? Because we draw from the prior distribution pi omega. But then, of course, we'll have access to some training data So we'll have a bunch of pairs x and y's. So what we'll do is that we'll use this training data to update our beliefs, which means that we'll define or we'll try to estimate now the posterior distribution over the model parameters, omega, given this training data. And this, of course, by the Bayes rule, can be written as the ratio of the likelihood of the data for the model parameters times the prior over the evidence PD of the data, right? And once or if we manage to estimate this guy, then we can then obtain the posterior predictive distribution now, which is defined as the condition of y given x and the dataset D. And this is defined in the same way as before for the prior predictive distribution. So you integrate over all possible parameterization omega of the neural networks that you consider, and then for each of them you look at the py given x under this parameterization, except that the weight that you put in front of each one of these predictions now is specified by the posterior pi omega given d instead of the prior pi omega. Okay, so this seems something quite easy, and it's just an application of the Bayes rule. But actually, it's quite, this remains a challenge in today's deep learning. And the reason is that computing the posterior distribution here is something very, very complicated. There are, in this case, two sources of difficulty. The first one is that you would have to be able to maybe estimate the model, the evidence of the training data, and that implicitly means that you would need to integrate all possible configurations of the neural network. And this is just gigantic because for the kind of neural networks that we are using today, they are made of millions of parameters. And so that means we would need to integrate over a space of millions of dimensions, right? And there is no way we'll be able to do that. And the second reason is precisely tied to this fact that the dimension of this distribution is equal to the number of parameters that we have in the neural network, which is in the millions or even more. And that makes things very complicated. You could still try to numerically approximate this, and that's what we'll do. But the sheer size of this space makes most algorithms quite poor, even though with enough training budget and blah blah blah, blah you can show that you could reach a regime where the approximation will become better and better. But this is just so far away from what you can do in practice, then it remains a very difficult problem. All right. Okay, so main message is that, okay, this is easy to formulate, it's just the Bayes rule, but computing this posterior is something out of reach if you were just to apply naively the Bayes rule. So we need to rely on numerical approximations if we want to compute this posterior predictive distribution. And so there are different ways you can approach this problem. In this lecture, I've chosen to reuse what we've seen before when we talked about VAEs and to use variational inference to build an approximate version of the posterior. Right? So we'll define our approximation Q of the posterior. So I will say that Q is a distribution over omega that depends on some variational parameters nu. And what we'll try to do, of course, is to adjust the parameters nu such that Q will converge towards the posterior P omega given the training data. Right? So we could say that, okay, we'll do that by minimizing, for example, the KL divergence between Q and P, right, with respect to the variation parameter. And as we have seen before, this is really the same development, so I will not take too long to explain that, but it corresponds, it's minimizing the KL, then it's identical to maximizing the evidence lower bound, the elbow, which, if you remember, is defined as the expected log likelihood of the data, right, in expectation over the our approximation Q, minus the KL between Q and the prior. Okay, except that now we'll have an issue, which is this one. So when we want to maximize the elbow, we want to maximize this expectation, right? And or even in the KL, in both terms, what we have is an expectation over the distribution Q, right? Here it's explicit, but in the KL, you would also have the expectation over Q of the log ratio Q over P, right? So it's still an expectation over Q. But since omega is so large, then there is no way we'll be able to compute this integral or these expectations exactly. So again, we need to approximate. And what we'll do is that even though we cannot approximate it, we'll be able to minimize it by doing gradient descent. Remember, and here what we also have is the same problem that we had when we talked about VAEs, that we want to adjust the parameters of the Q distribution, which enters in the expectation here, right? And that's something we cannot do, because if you remember, the gradient of the expectation is not the expectation of the gradient, right? So we could try to use this reparametrization trick that we use for VAEs. What we'll do here today is simpler. We just approximate the expectation by using one single realization, and that will be enough then to produce a correct approximation, right? So we'll approximate the integral by first sampling a single omega from the Q distribution from the approximate posterior, and then we'll do one step of maximization. So we'll try to maximize the elbow by maximizing it over just this one single omega hat, right? And so we'll define an approximate loss with respect to the variation parameter, in which the expectation has been replaced by just the log likelihood of the data for that particular omega hat value. Okay, and the KL, depending on the choice that we do for Q, is something we'll be able either to have analytically or to approximate numerically. Okay, so in the context of Bayesian neural networks, this procedure, which is quite close to what we have seen for VAEs, is known as Bayes by backprop, which is due by Blundell in 2015. Okay, so this is something you could do, right? And at the end of the day, you would arrive to good parameters for Q, and then you could plug in this approximate posterior to compute or to approximate the posterior predictive distribution Py given X as the integral of Py given X and omega, but in which you would have replaced here the posterior P omega given D by this approximate Q. Okay, so this, maybe you would find this a bit complicated and obscure. There is actually another way to approximate the posterior predictive distribution, and which is given by another procedure which is known as dropout. So dropout is actually something quite interesting because at first it was proposed for quite a different objective. So it's an empirical technique that was originally designed to avoid overfitting in neural networks. And the idea was quite simple, would be that at each training step, meaning at each for each sample in a mini batch, right? What the procedure was about, it was about removing each node in the network with some probability p, right? And then to update the weights of the remaining node by backpropagation as usual. And so at every step, you do as if some of the nodes were removed from the network. And these nodes that would be removed at random. So at the next step, it would be another random subset of nodes that would be removed, and you would proceed like this and like this. And the purpose or the intuitive motivation was to basically force the network to have multiple nodes that are able to detect the important patterns, or to detect the features, or to learn the features that are important for eventually making the prediction. Instead of just having maybe just a few or even one single node that is able to capture or or to produce good prediction, because that could also just be an artifact of the training data and therefore lead to overfitting. And so if you insert dropout layers in your architecture, then you would do this, you'd follow this procedure when you train it. And then when you test, when you want to make predictions for test data, then of course you would want to use the entire network. So there are two ways, there are two procedures that you could use when it comes to making predictions. The first one is simply to make predictions using the trained network without dropout, but by rescaling the weights by the dropout probability p. And this is the procedure which was originally defined in the paper. But this is actually not very or very strongly principled in my opinion, because this is not exactly how the network was trained in the first place. The network was trained by just taking this random subset of the node and then making predictions. So a better principled solution, even though it's slower, is to sample T neural networks using dropouts. So you have your architecture, you have the ways that you've learned, blah, 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 blah. And when you want to make prediction, you just sample T random configurations of this neural network in terms of the nodes that you are using for making the predictions. And then for each of them, you make a prediction, and then you aggregate all these predictions together, and that forms the final predictions of the network. Right? And this is now one-to-one with how you train the network. And indeed, when it comes to trying to minimize overfitting or improving generalization, then dropout has proven to be quite effective. And so this is a plot that comes with the paper. And you see that indeed, without dropout, the training is quickly saturating around 1.75 classification error. But if you do this trick of inserting dropout layers, then you can reduce the error further by almost 1 point. Then you may wonder, but why does it work, right? Why would it be a good idea to randomly remove nodes and then to train the network or this random subset of the network only? So The first reason is that it makes the learned weights of a node to be less sensitive to the weights of the other node, right? Because when it's trained, it's trained in different situations in which sometimes some of the other neighboring node or some of the nodes in the previous layer are activated, some other times they are not. And so the particular node has to learn to cope with this, right? And so that's why they become less sensitive to the weights of the other nodes. And the effect of that is that it will force the network to learn basically several independent representations of the patterns, and because of that will decrease overfitting. Another explanation which I like better is that actually dropout is approximating Bayesian model averaging. Implicitly, when you do dropout, you are implicitly when you do dropout, what you are basically computing is something which is similar to this posterior predictive distribution. Because effectively what you're doing is that you are sampling parameters value from some distribution, which in this case is defined by the dropout procedure. And then for this particular configuration of the network, you compute its prediction, and then you repeat that a few times. So basically you approximate this integral by doing that, repeating this process t times. That gives you an approximation of this posterior predictive distribution, right? It's also very connected to ensemble methods that I'm quite sure you've seen in Introduction to Machine Learning, in which the idea is to make predictions. You do not only use a single model, but you aggregate the predictions of several models together. And that is also shown to reduce overfitting. Here it's more or less the same, but extended up to an infinite distribution, or extended to infinitely many models or instances of a model, in this case neural networks. Okay. Okay, so this was for the intuitive explanation. I just said that it was doing something similar to Bayesian model averaging. Actually, and this is a quite nice result, I believe. It is doing Bayesian model averaging, and this is what we show. That dropout is actually doing variational inference in the way we've defined it earlier. And so if I'm claiming that dropout is doing variational inference, what I have to show you is that there is some variational family Q that I could define, and if I were then to follow the Bayes backprop procedure for this particular family of distribution, that would be exactly similar to minimizing the regular loss, but with dropout layers. And this is what I will show. So first, I will just introduce a few notations. So I will split the weights omega for the different layers, right? So I'll assume that we have L layers from 1 to L, and the parameters of these layers are denoted by the matrices W1, W2, WL. And each of these matrices will be further split into vectors. So Wi, capital Wi will be divided into a bunch, will be defined as a bunch of vectors, Wi1, Wi2, up to Wiqi, where Qi is the number of nodes in, or the width of the layer. Then we'll also define variational parameters nu, and we'll define them in the same way, and we'll denote them by the M notations. So we'll have a bunch of M matrices, and then each of them will be defined by vectors. And then I will say that I will define Q over omega, depending on the parameterization nu of the variational family, as follows. So I will say that Q omega is factored as the product over the layers of other distributions over the weights for the layer I. So that corresponds to the matrices Wi, and that this distribution QWI will depend, of course, on the parameters for that layer, the corresponding parameters for that layer will be specified by the corresponding variational parameters associated to the layer, meaning by mi. Okay, and then this distribution over matrices will be further factored as a product of distributions over vectors, right? And then we'll say that the QWIK are defined as a mixture of two Dirac distributions, multivariate Dirac distributions, one which is centered at 0 and one which is centered at MIK. And this mixture will have as weights, as coefficients, P and 1 minus P. So this is just saying that if you look at some node in layer I, and that node has the index k, right? Then all the weights connected to this node are having onto this node either take, and so all these weights are defined by this vector Wik, right? They will either take the multivariate value of 0, right? And so this is this first term, and they will take a value of 0 with probability p, or they will take a value, another value with probability 1 minus p, and that other value would be given by ik. Okay? Now, given the previous definition for the variable family Q, sampling parameters omega hat will be done as follows. Because remember, when you want to do variational inference, we want to follow this base backprop procedure. So that means we have to do these two steps. And the first one is to be able to sample some value omega hat from Q. Okay? So the way we would do that, where am I? Yes. would be to simply draw binary variable zik from some Bernoulli distribution of parameters 1 minus p for each layer I and each unit k, and then to compute wi, right? The one that I'm sampling from the Q as the product of mi times some diagonal matrix made of the zik values that I've just drawn at the previous step. That will be the same as just saying that you are using for wi the matrix mi, in which you have set some of the columns to 0, and you have done that with some probability p. Right? And that's just the same as saying I'm disabling this node ik with some probability p, and when I say I'm disabling it, that means I'm just setting all the ways connected to it to 0. Right? This is what happens when you effectively do that. Right? And when I say it like this, but this is just strictly equivalent to dropout, right? Which is about removing units from the network with probability p. Okay. Okay, so now let's proceed. And so one step of stochastic gradient descent on the elbow, as we would like to do when we run base backprop, would look like this. First, we sample some omega hat from Q, right? But I've just shown you here that this is just the same as randomly setting units to the network to 0, and that's just what you do when you do dropout. And then you still have the second step, which is the step of doing one gradient step of maximization over this loss, which is in which you want to maximize the log likelihood of the data for that particular configuration of the parameters minus the KL of between Q and P. Right? But actually, maximizing this is the same as, is really equivalent. I mean, maximizing L hat over the variational parameters, of course, is the same as minimizing minus this expression, right? So minimizing minus L hat being equal to now minimizing minus the log of the data, minimizing the negative log likelihood of the data plus the KL between Q and P. Right? So this is, I'm just flipping the signs, right? But this is nice because now what you should see is that this first term that now we want to minimize is just the typical objective that we are interested in when we do regular training of a network, right? Because typically if you are doing, for example, classification, then this will result in the cross entropy, right? So the negative log likelihood of the data will be the cross entropy, and that's just this term. Right? It's the same also as we did for the mixture density network, and in all the previous networks that we've seen together, I've always started from the generative model, and then we arrive to, and then we apply the principle of maximum likelihood estimation, which we transform into a minimization of the log of the likelihood. And that's just this term, right? So that's the same. We still have a second term, right, which appears, which shows that there is still a difference between regular training and doing variational inference. But actually, but this term is special because it's a term which is enforcing the posterior to remain as close as possible to the prior, right? Because you want to minimize the KL between the posterior, the approximate posterior, and P. And depending on the assumptions that you have, or depending on the prior, this can be rewritten in several ways. And what is interesting to notice is that if you start with, for example, a Gaussian prior on the model parameter, then this KL will actually be equivalent of saying that you apply L2 regularization on the weight of the neural network. Right? And similarly, if you say that your prior beliefs are Laplacian over the model parameters instead of Gaussian, then minimizing the KL now between the posterior and this Laplacian prior will be equivalent to L1 regularization. Right? So again, this is just to stress that, or for you to see and understand that a lot from machine learning, when it comes to specifying a loss and maybe some regularization that you apply, a lot of these things can be connected back to a choice of generative model and also a choice of prior if you are being Bayesian about that. And this is one of these examples where I'm just showing you that minimizing the cross entropy plus the L2 regularization would be equivalent to say that you want to do Bayesian posterior inference starting from a Gaussian prior. And then when you minimize the loss, what you are actually doing is that you are trying to optimize the parameters of the variational parameters of this approximate Q. Okay, so this is just what I said actually. So this shows that indeed when you train a network with dropout with a standard classification or regression objective, what you are actually implicitly doing is variational inference to match the posterior distribution of the weights. Okay, so just a few more things. So now that we have a procedure which is actually the same procedure as we've been using before to train neural networks. So the main message is this one, by the way. You can actually obtain Bayesian neural networks by just following the same recipe as the one you've learned, and I'm quite sure already applied in your project, doing stochastic gradient descent on the cross entropy loss, except that you can add now, for example, dropout layers, and maybe some regularization term in the loss or regularization penalty into the loss. And if you do that, then you can upgrade your prediction to a full posterior predictive distribution, right? And therefore to capture some epistemic uncertainty at the same time. Okay. And so precisely how do we then get estimates for the epistemic or the uncertainty from these neural networks with dropout layers? Well, the way we would do that would be to draw T set of network parameters from the variational posterior Q. So you just draw T random neural networks depending on where you put the dropout layers. You would compute the predictions for these T networks, right? And then you would approximate that posterior predictive distribution, and so you could say that you would have so from this you could compute like statistics, like the first and the second moment, and so the mean would be simply the empirical mean, and the variance of the output would be given by the variance of the predictions plus the sigma squared, which is the noise that you would assume, the irreducible noise that you would assume here. Okay, so let's do another demo of this. Okay. Where is it? All right. So what you will see here is just, so you have some training data, and then you have some mean and variance that are estimated in the way I've just described, using trying to do variational inference, for example, with dropout layers. And you would start with some prior beliefs about the weights, and then you train and train and train your network. Eventually it would reach some optimum, and that would be now the predictive distribution that you obtain. And you see that the uncertainty is different depending on the input. You would have high uncertainty in regions in which you don't have any training data, and that's expected because these are regions where the data is not putting any constraints with respect to your prior beliefs. And actually, as you go further and further and further away from the training data, then you will have a behavior which is closer and closer to your prior predictive distribution. And it's only close or in the vicinity of the training data that the posterior distribution will be different and much or less different than the prior predictive distribution. So we could add maybe more point like this. And you see that, yeah, we'll see what happens. How is it? Let's restart the training. So maybe you would have expected the blue regions to span over all the training points, right? But it's not the case. So it's very important to understand why. It's because here we are only, I believe in this demo, they are only trying to estimate the epistemic uncertainty, right? And they are not trying to, at the same time, model the aleatoric uncertainty. And in this case, the aleatoric uncertainty would be high, and that would be because this represents noise in the true process. If you add we have samples from the true distribution py given x, and it's going all over the place, and that's something that can only be captured by the aleatoric uncertainty, but not by the epistemic uncertainty, which is only capturing our ignorance or beliefs about the model itself. Okay? All right. Okay, so this is another picture with the more or less from the same paper, if I'm not mistaken, as one of the earlier figures from this morning, in which so it's showing the input image. Okay, and so the problem here is to take an image as input, right, and to produce as output a regression map in which each pixel is labeled with the depth in the scene. So basically, for example, if you look at this one, it amounts to say that these pixels correspond to things that are closer to the observer than the pixel here, because they correspond to stuff like trees that are really far away from the observer. Okay, and so to learn this, they use a depth camera, and they will basically try to learn a mapping between these RGB images and the depth map from the depth camera. You see that they are black pixels because they either in this case correspond to things that are too far away for the depth camera. Usually depth cameras have a limited range, and then beyond this range, they are not able to produce prediction. So you just get the maximum value in this case. Then the column in the middle corresponds to the prediction of the model, and then the two last columns correspond to the aleatoric uncertainty and the epistemic uncertainty. And again, as before, you see that aleatoric uncertainty is high for the pixels that are very far away, or when there is or at the boundaries of the object. So here it's a bit all over the place because of the trees, and of course the trees are very large, have a large volume, and they occupy quite a large space. And so it's difficult to properly identify where is a leaf in this 3D space. So that's why you have this amount of noise in this region. And here, the last column is about the epistemic uncertainty, which captures the ignorance of the model. And so what is there to say? yeah, it's a bit more difficult to discuss. They say that aleatoric uncertainty is prevalent around depth edges or distant points, as I said. And they say that Make3D does not provide labels for depth greater than 70 meters. Therefore, these distances dominate the epistemic uncertainty signal. Okay, which is why this point far away have large epistemic uncertainty. So what time is it? Okay. So I will skip this part, but I recommend you to go over it. It's just extending. So it's connected to what we have just seen with Bayesian neural networks. So you start from an architecture of neural network, and then you posit some distribution over the parameters of this neural network, and we've seen then how to compute the posterior given the data, and then use that for the posterior predictive distribution. There is an interesting development to do when you further assume that the width of this neural network becomes infinite, right? If you do that, and on top of these weights or infinitely many weights, you put a distribution, right? Then what you obtain is known as a Bayesian infinite network. And you can read the slides, but the main message is that eventually, and this is actually one of a very fundamental result in neural networks, is that the mathematical object that you will then obtain is a Gaussian process. And so it shows that there is a deep connection between multilinear perceptron of infinite width and Gaussian process. And eventually, the MLP will vanish into or will become a Gaussian process. So a Gaussian process is a distribution over functions or vector of infinite dimensions. And this distribution over these infinite things is just a big Gaussian distribution. Anyway. All right. So I will do a last break and we can resume at, let's do 11:45 to talk about the very last chapter for the course, adversarial attacks. All right, so welcome back for the last part about adversarial attacks. So as you will see, it's a bit different and quite different from the stuff I've been talking about today. But still, I decided to put it into the same, in the scope of this lecture, because I think they are quite important to, it's something that should, I mean, you should really be aware of when it comes to the robustness or the expected robustness of the networks of the neural networks that you want to have. So robustness is something that you could achieve by just accounting for different types of uncertainty, as we have seen. But maybe there are also situations in which the neural networks that you're using are not actually as robust as you want them to do. And this is precisely what we'll see now with adversarial attacks. So it all started basically by a paper written in 2013, which was titled "Intriguing Properties of Neural Networks." And what they notice, what they say, and I will just quote them, is that we can basically cause the neural net, some network, any network, to misclassify an image by applying a certain hardly perceivable perturbation, which is found by maximizing the network's prediction error. In addition, the specific nature of this perturbation is not a random artifact of learning, and the same perturbation can cause a different network that was trained on a different subset of the dataset to misclassify the same input. So they say then that the existence of these so-called adversarial negatives appears to be in contradiction with the network's ability to achieve high generalization performance. Indeed, if the network can generalize well, how can it be confused by these traditional negatives, which are indistinguishable from the regular examples? So, just to illustrate, this is precisely what they show to happen. If you start with a regular image, for example, of a pig, and your classifier says, I'm confident this is a pig, and indeed that's a correct prediction. If you produce a new image, an adversarial negative, which is a composition of this original image plus this noise, but with a very small magnitude of 0.005, that produces for the human eye something which is the same or almost the same as the original image, right? So these two images are actually distinct. If you could look at the pixel values, they would be different. And actually, for the neural networks, they are so different that the prediction now for this image become an airliner instead of a pig. This is precisely the phenomenon that they observe in this paper, and that they call adversarial attacks. So, of course, there are plenty of other examples. These are other examples in which you have the picture of a bus, of this bird, and of some kind of pyramid. And when you add this noise with some very small magnitude, that produces these new three images. And for the class, I think it was AlexNet in this case, then AlexNet predict that these three images correspond to ostriches. Of course, this is plain wrong. So what they say is that this seems in contradiction to the empirical observation that neural network appears to be so good at computer vision, and they appear to have strong generalization performance. Indeed, they perform very well on test data, and this has been proven on a wide set of benchmarks. But if that is true, how can we at the same time have these issues, these adversarial examples? What's the reason? What's the fundamental reason? And they show that, okay, this is the case, and these are other papers. This is the case for images, but this is, and so ConvNet but this is also true for other kinds of networks, even those that would have to produce some structured output, like segmentation network or pose estimation networks. And here, this is what they do. So at the top, you have some input image. You have the original segmentation output. I don't know exactly which model, but I suppose it's some kind of, for example, UNet that is producing this segmentation map. And then what they do is that they craft some adversarial attack to produce this now compromised image. And they are able to craft this attack to basically force the network to produce anything that they want. It's not only that they're making wrong predictions, it's the fact that they can drive the network to make any predictions that they want. In this case, to produce this minion segmentation map. The same for pose estimation. You can fool the network to produce quite different or just target just a target pose as you wish. Okay. So one thing that you may say is that okay, but actually this problem is artificial, and in reality, when I will feed to my neural network a video stream, for example, because I want to, I don't know, I have a system that would be tracking cars and other things. Because of the imperfection of the camera, these small perturbations that I'm adding, they would be basically cleaned up, and there is no way that on a real system this would work. Well, you would be wrong, and quite wrong. So what you will see in this video, and just to show you the extent of this problem, is that here in this video, what these researchers did was to take an original image, add one of these adversarial perturbation, right? And then to actually print out these adversarial images on actual paper, and then to take pictures with a cell phone of these printed images. And what you will see is that even though it's now passing through this corruption process or destructive process of printing the image on paper and then taking images of these printed images through the cell phone, I mean, a lot of information is expected to be lost, including these adversarial perturbations. But this is not happening, unfortunately. So this should be predicted as libraries, and this is the correct prediction. But the adversarial version now is predicted as a prison. This is a washing machine. It's correctly predicted as a washer. But this one is a doormat, which is wrong. And you see that it's doing, I don't know if you could see the numbers which correspond to the confidence of the prediction. They were still quite high, above 30%, among, I suppose in this case, 1,000 different outcomes. So washer with 40% accuracy on a non-compromised image. Now it's classified as a switch with 26% confidence. They also do that for this. This is another example where they print an adversarial negative. And so this is a cat. It looks indeed fishy. I mean, it's quite obvious that there is something happening with this, but the network is confusing this cat for, in this case, a desktop computer. and it's producing predictions with very high confidence. You see that it's going between 90% confidence and 50% confidence, which is quite wrong. The same for this one, where what they do is that they print some texture that they apply on in this case, a 3D object like a turtle. They've designed the texture of the shell of the turtle such that a neural network would think, I don't know if you could see, would think or would predict that it's a rifle, and of course this is a plain wrong prediction. Of course it's not like here. Yes. But it's just a turtle for us. But the network think with high confidence it's not, and it's a rifle. And you see that the next significant predictions are not even about turtles. The next one is a revolver, which is still a kind of rifle, an assault rifle, a holster, and then a bow. So plain wrong. So how do we build this? This is something I've not told you. How do we build this adversarial example? Well, one simple thing to do is to solve this minimization problem, in which you start with some neural network F that comes with some parameters theta that you've obtained by regular training. Then you have some input image, a non-compromised image. And then what you want to find is a perturbation R that you would add, so some noise that you would add to the input image, such that the output of the neural network for this compromised image minimizes some loss for some y value of your choosing. And in particular, of course, as the attacker, you could say that the target y is a class label which is different, of course, than the correct label that you should associate with x. So for example, you could say that x is this image of a turtle, but y is the class for the rifle. And what you want is to find the perturbation, a small perturbation that would modify the output of the network as such. And you would want to minimize this problem under a constraint, which is the fact that the perturbation R should remain small, right? So the norm of this perturbation, for some definition of the norm, you pick your favorite norm, should remain lower than some threshold that you set. Okay, and that will force the network basically to, but yeah, it will be limited in this search space, and it would try to identify a good R by minimizing this problem. So you'd think that this should not work, right? Because if you just think about how a neural network should be able to generalize, right? What should intuitively and what actually happens is that if you take an image, right, and for this image, the network is making some correct prediction, you would expect, and this is what happens, that in the immediate vicinity, in the immediate neighborhood, so of that image, that the prediction of the network do not change, right? And in particular, if you view the image as some point in some high dimensional space, then you could put these images into there would be some kind of ball around these images, right? And you would expect that everywhere in this volume, the the output of the neural network would not change and would remain of the correct class, of course, right? Because we are making and trying to leverage this principle of local generalization. Everywhere in the neighborhood of my training data, I should be able to generalize, right? And indeed, this is what we observe in practice, that neural networks are able to generalize very well. But still, if you solve this problem, even if you remain in the vicinity of the network, you will be able to find these adversarial perturbations. And so, yeah, I will come to that later, but this is still actually an open question in the field. Why does this precisely happen? There are several hypotheses, some of them more or less convincing, but we still don't understand everything from this. And more importantly, we don't know how to fix this problem, right? So I think it's important that you have this in mind, or at least that you are aware of that, because these adversarial attacks, they pose, in my opinion, a very strong security threat to any system that would make use of machine learning or deep learning, right? In particular in the real world. So every time, for example, so examples where this could be problematic would be if you are making use of classifiers to produce predictions, then this classifier would be prone to these attacks. And if this is just one step of a more complicated system, then you don't want an attacker to be able to compromise this step, because this maybe could have some cascading effect with respect to the entire system. And this is quite an issue, because also more and more, most of the software industry is relying more and more on neural network to just have better system because it works better. But at the same time, they have these vulnerabilities, and they really pose a fundamental issue. So that's the case also, for example, for malware detectors, like antiviruses. More and more now they are using neural networks to basically detect malwares. But if these neural networks are prone to adversarial attacks, then that means the creator of these malwares possibly have a way could fool them and then bypass the defense that you want to have. Also, I think this one is quite important. So, and I will use this. So let's imagine that you have implemented, or you are just inside a self-driving car. It's driving, you don't have control. And of course, the car is making sense of its environment. It's full of neural network to do that. But what if some attacker put some stickers maybe on the traffic signs, and these stickers were crafted in such a way that they would change the outcome of the neural networks inside the car, right? And that's something that has proven to be a problem in practice. At least some have demonstrated that this could happen, and therefore that makes that's a big issue, a big security issue, because someone could basically take control of the car this is of course oversimplifying, but by changing or making modifications to the environment, that could have an effect, and a strong effect on how all the systems behave, and so on. All right. So, as I said, this phenomenon is still a bit mysterious, but there are several hypotheses, several assumptions that try to explain the origins of this vulnerability. The first one, and all of them are still conjecture, so it's very hypothetical what I'm saying here today. But one of the first conjecture is due to overfitting. And by that, I mean that, for example, if you look at systems that take as input images, natural images, they are indeed correctly classified. So that means natural images are put within the correct regions in the pixel space. But at the same time, they are very likely, and this is the hypothesis, to be close from the boundary of these regions. And they are sufficiently close for these random perturbations to exist in practice. And indeed, that makes sense. If you remember that you are dealing with very high dimensional space, in this case, the space of images of, I don't know, 1000 by 1000 pixels of 3 colors, that's a 3 million dimensional space. It's very likely that the image in this space is close, at least from one of these stream of 3 million dimensions to the boundary. And so it seems it's just statistic at this point. It's very likely that this will, one of the pixel will be close to the boundary. And therefore, if you identify this pixel and just make a random perturbations to this, maybe one or a few of them, that will flip or that will change the output of the network. Another conjecture is the one of excessive linearity. And basically, it's to remember that if you look at the decision boundary of deep learning models, most of them are piecewise linear. So this is typically what you will obtain when you put ReLU activations everywhere in your neural network. At the end of the day, you will have a function in with respect to the input space, which is piecewise linear. Right? So that means there will be regions in the input space where everywhere within this region, the output of the network will be just a line or an hyperplane. Right? Then that means that for some adversarial example, for an adversarial sample x hat, its dot product with a weight vector, right, is such that, so I'm just saying, if the model is indeed linear, that means I can rewrite, I can express the output of the model as a linear operator. So as a dot product of some vector, a weight vector w times the input x hat. And so when x hat is an adversarial sample, that means that this quantity decomposes as the sum of the decision or the outcome for the uncompromised original input, wt times x, plus the contribution of the perturbation r. Right? And so that means effectively, right, it's quite obvious, that this adversarial perturbation will cause the activation to grow by this quantity, by this amount, w transpose times the perturbation. Now, if R is a small perturbation, right, and for example, if it is something which is defined as some epsilon quantity with epsilon small times just the sign, so plus or minus 1 w, right? And if w has n dimensions and the average magnitude of an element is m, so the average magnitude of the average magnitude of w, so if an element of w is m, then that means that this activation, that the activation with respect to the original value will grow by an amount which is proportional to epsilon times m times n, right? And so since we are dealing with very high dimensional problem, even if epsilon is small, right, because n is large, right, even a tiny perturbation may have a large effect because this can grow, this can become big very quickly. And if this becomes big very quickly, that means that even though you are making just small perturbations to the input, there will be some kind of cascading effect when it forward propagates through the network, and these small perturbations will be amplified by a large factor, and will be so amplified that they will be able to change the output of the network. And so this is what they show in one of this, in a paper, I don't remember which one, but studying this hypothesis. And they show that indeed neural network produce responses over this epsilon, the quantity of the noise, of the magnitude of the perturbation rather, which is almost linear, right? And so what they show are the logits for 10 different classes. So the logits are just this quantity that arrives just before the softmax layer, right? And they show that even with, the epsilon do not need to be small for the quantity to have a large effect, right? If you look at, so you should consider the scale here, which go from -400 to 800. And you see that if you go from, even close to 0, here, for example, you can see the black line. Very quickly, even with epsilon not larger than 1, 2 maybe, I don't know, that can basically flip the quantity, which was around here for epsilon negative, and then as you add the perturbation, it's really going in the opposite direction, meaning that since this is the input of the softmax, you will basically, that class will contribute more to the, and will be the one which is selected by the network. But wait, what are you saying? Okay. Okay, so there is one good question by Margot. Is it possible to retrain the neural networks based on those new compromised images? Does it improve the situation, or such perturbations will still exist? So that's a very good idea, and this is what I was about to talk about. So how can you, so we know, we observe that neural networks are prone to this attack, they are vulnerable to these attacks. Can we defend them against these attacks? And so of course, there is a bunch of countermeasures that have been proposed during the last years. Most of them are about doing some kind of clever data augmentation. Another family of method is what you just described, to do adversarial training. And it's basically adding into the training set adversarial examples, others, and you will see that it works to some extent, but it's not perfect, and it's actually it's not the case at all. Actually, it's quite fragile, and other techniques also involve denoising and smoothing. Okay, so I will not go into too many details. I will just describe one of these methods, and I will tell you then why I only describe one of them. But I picked this one, denoising, because it's one which has proven to be quite effective. So in 2017, there was a challenge which was organized among machine learning researchers. and there were two tracks to the challenge. First, to come with algorithms that would be the best attackers, so the attacks that would work on a wide variety of networks. And the second track was about proposing defense mechanisms that we could add to the networks to make them more robust to any kind of attacks. And then, of course, the challenge was organized such that the two sets of algorithms were actually competing against each other. So the winning thing for the defense track basically based or proposed a solution on the concept of denoising with some kind of UNet architecture. And the purpose was to basically train a neural network to take as input an image, in particular images with these perturbations, these adversarial perturbations, and then to produce as output images that would have been cleaned from this, that would have been cleaned up, that would have been denoised from these perturbations. And then these these images, where are they, by the way, that you would get as the output of this UNet architecture would then be fed to the actual neural network that should make a prediction for that image. So this proved to work quite well. In the challenge, of course, approaches similar to what you suggested were also evaluated, like adding adversarial example to the training set. But actually what happens is you are just moving the problem away a bit further. Now the network would become more robust against these particular attacks, but that does not mean there are not other algorithms, other types of attacks that would work well against this same network. And so after the challenge, they wrote a paper to summarize the solutions and then to try to get some more general conclusions. And one of them is as follows. In this paper, we evaluate 10 proposed defenses and demonstrate that none of them are able to withstand a white box attack. And we do this by constructing defense-specific losses function that we minimize with a strong iterative attack algorithm. And with this attack, on Cypher, an adversary can create imperceptible adversarial example for each defense. By studying these 10 defenses, we have drawn 2 lessons. First, existing defenses lack thorough security evaluations, and adversarial examples are actually much more difficult to detect than previously recruited. So they are basically saying that, okay, we still don't know how to solve this problem. We don't have the perfect solution or good enough, or just even a good enough solution yet. And in another paper, some other authors are saying no method of defending against adversarial example is yet completely satisfactory. This remains a rapidly evolving research area. So I've not looked into the recent literature, but we still see plenty of papers trying on this topic, adversarial examples and adversarial defenses, and I'm quite confident to tell you that this is still a major problem in the field. We acknowledge that this is a problem, but we don't have a solution for that yet. All right. So with this, I want to conclude this lecture for today. Again, the main outcome, the take-home message from this lecture is that, in my opinion, you should always think about uncertainty. You should always think about all the things you don't know about your problem, and you should account for them in your results, in your approach, in your modeling, be it in scientific disciplines or engineering disciplines. But also at the same time, the last part of today's lecture you should be aware that even though these neural networks, they work very well on plenty of problems and they reach superhuman performance on many tasks, they are still, in my opinion, quite fragile. There are plenty of situations where you can force the network to fail. And that's something that you should be aware of if you ever have to deploy or design and build a system around this technology. All right. So I also want to give you some closing remarks. So I'll just prepare a few more slides that will be quick about that. All right, so today was the final lecture. So I hope that you had a lot of fun in learning about deep learning, in doing your project, even though I assume it's not done yet. You still have some work to do. But I hope that you learn a few new concepts, that you discover this field, and that you had fun along the way. So in my opinion, we did quite a lot together. So if we summarize what we have seen since the beginning of this course, so there was a first part of the course, I would say, dedicated to the fundamentals of deep learnings. So from basic concept from statistical learning theory, then from this we built the multi-layer perceptrons. We saw together the recipe for training, and then building this network, architecturing these networks together. And then we had a lecture on automatic differentiation, which is this family of algorithms that you can use to automatically evaluate gradients exactly from this composition of differentiable functions that we have in neural networks. And then moving on in lecture 4 to optimization algorithms to train these guys. And then from there on, we had 7 more lectures on, I would say, more advanced topics, or I would say use cases in which you can apply neural networks. So we had a first track on, I would say, vision or dealing with images, of course, with convolutional neural networks, and then with more advanced architectures for computer vision and tasks like segmentation, object detection, and so on. Then in lecture 7 and 8, we dealt with sequential data, like we typically have in natural language processing, but the same architecture actually apply to a bunch, of course, of other kind of data, as long as they can be framed as sequences. And then finally, we had the 3 last lecture about generative models. First variational autoencoders, then GANs, and then today with uncertainty. I would say it's the same kind of, it's in the same scope, because you can view this network that we have seen today in the first part of today's lecture as some kind of simple generative model or probabilistic model from between the output and the input. Yeah, you will have noticed that I eventually skipped a last lecture about deep reinforcement learning. I think we already covered enough materials this year. So this is why I decided to just skip entirely the lecture on deep reinforcement learning. Of course, if you are curious about this topic, then I invite you to attend other courses. There is a course on this topic by Damien Ernst, and there are also plenty of other courses online that you can find. About the exam, just a few practical details. I will send an email in a few days, but I can already tell you that during the oral exam, you will have 3 types of questions. You will have a first main question about the fundamentals of deep learning, so something related to these foundations from lecture 1 to 4, and then you will have another question on one of these 7 other lectures from 5 to 11. And the reason I'm doing that is that I want to make sure that that at least you know the basics, you know how to architecture a neural network, you know what it means to compose these layers, how to get the gradients from these neural networks, and then how to train these guys. That's, in my opinion, the basics. at the end of a deep learning course, I believe you need to know that. And then we'll dive into the more advanced topics. And we'll see the kind of questions you will draw. I will certainly also send you example of questions, more specific questions I will ask, so that you can better identify what is important and what is not. I realize there are a lot of slides in the material, but there are plenty of slides that do not need to be studied actually, and you will be able to identify those by these questions. And finally, also as part of the exam, I will ask or maybe the teaching assistant 1 or 2 short technical questions about your projects. And so this could include questions about, I don't know, why did you pick this architecture, this number of layers, what's the effect of this or that, or maybe even some questions related to the code that you wrote. We will be asking these questions because unfortunately we realized from previous years that some of you they passed the exam and they passed the course, and then we realized, but actually they still don't know how to write a neural network, and they still don't know how to code a neural network and train it. And when we realized that, okay, there is something wrong here, and we want really the student to be at least to be able to do that. So we'll check for this at the exam. This will not be very deep and technical question, just the basics, but we want to be sure that you know the basics. Okay, so if you are interested, you have become more and more interested in AI, in deep learning. I think now, having followed this course, you should be well covered, and you should know by yourself where to know more about this. If you look at the program, at the courses that we have at ULiège on machine learning, there are a few more courses that I could recommend you to follow. So if you are still in Master 1 and you will have to decide the classes that you attend next year, I would recommend following Advanced Machine Learning, which is an introduction to research in machine learning. And it's quite different from typical lectures that we teach you, like here in this course in deep learning, in the sense that it's more about reading scientific paper, discussing this paper, maybe watching a seminar and tutorials together. It's also about you summarizing scientific paper and then presenting them to the class. But the point is that this course, at least the materials that are covered, they are really at the frontier of the knowledge in the field. We are really just using almost raw materials from the scientific literature. Then there is a course, as I mentioned already, about reinforcement learning, optimal decision making for complex problems. I believe that as more and more reinforcement learning algorithms are combining tools from deep learning, it's maybe best to first follow deep learning and then to follow the next year with reinforcement learning. There are also other courses in which, of course, you do not need necessarily deep learning to succeed, but having followed deep learning could be a plus. And so I'm thinking about introduction to intelligent robotics and computer visions. Both of them, if you look at today's scientific literature, they are more and more using deep learning to solve the tasks that they care about. Okay, then another thing that I wanted to mention, so I don't know exactly the population of the students I'm talking to, but I suppose many of you are still in your first year of master, and next year you will have to pick a topic for your master thesis. You should know that you should really feel free to contact us if you just want to discuss topics. If you're interested in doing deep learning and would like to do a master thesis on this topic, really feel free to write us an email and we can just have a chat to discuss about your ideas or topics we may have on our side and that maybe could interest you. Also, if some of you are interested in doing research in deep learning, you should also feel free to contact us. Every year we have some opportunities for funding PhD students. Not every year, but it is usually the case. So also feel free to contact us if you just want to discuss about these opportunities. All right, and then finally, the last word I will have about the course and the content that we have covered together is that really, in my opinion, artificial intelligence and deep learning, they are really transforming, of course, software engineering. I suppose most of you are computer scientists or computer engineers, and that's one, of course, of the main and most obvious application of deep learning. It's within software engineering. But what you should also realize, I suppose, as engineer and scientist, is that deep learning is also transforming more largely science, engineering, and even society. So in increasingly many disciplines, deep learning is being used, and I think because of that, as future engineers and scientists yourself, the skills that you have learned, or you will have learned once you will have studied this course, really these skills that you will have acquired, if you look at today's market, there are still only quite a few people that know how to do deep learning. And so you really have some kind of unique asset, some kind of unique skills, and I believe they can offer you opportunities to do great things. And in particular, of course, there will be applications in classical software engineering. But I think, in my opinion, the most interesting and biggest challenges or opportunities for AI, they lie outside of software engineering. And so you should look at what happens in physical sciences, what happens in more classical engineering disciplines, what happens, I don't know, in education, in sustainable development. There are plenty of opportunities, in my opinion, to apply AI and deep learning in this field. And I think this is where it will be the most exciting and the most important. And I believe, even though you may have been trained as computer scientists or computer engineers, you should think outside of this box and maybe explore these other applications. All right, so with that, that's all, folks. I hope that you had fun, and that's it for me. We'll see each other at the exam. So I will stay a few more minutes for questions if you have some. Okay, so there is one question in the chat. Is there any presentation of the project before the exam day? So this is actually still something I'm discussing with the TAs. I'm not quite sure, because the only day this would work would be on May 21st. Unfortunately, I'm not myself available in the morning. So I would need to discuss with a student representative if there would be another time where this could work. But in any case, if there is a presentation, as it was actually announced when we released the project, it will be short, like 5 or 10 minutes max for each presentation. I think it would be nice that you see each other presentation to see what your peers have been up to. It can give you ideas, or you're just curious, but it will be short, so that we could have we would schedule all I think we'll have about 20 presentations or 20 projects, but we'll try to schedule them all in half a day, either a morning or an afternoon. Yeah, and one last thing for those connected, thanks really also for connecting. It's been quite frustrating for me, to be honest, to talk to my screen for 11 lectures. I would really have appreciated to see you. I suppose it's the same for you. So thanks again for the 15 of you. We've been regular and connected every Friday. All right, so I don't see any other questions. See you at the exam, or maybe sooner.